Hello everyone. In this video, I'm going to talk about a problem that I encounter in my dynamics class a lot, and that is when you want to look at the velocities or find the velocities of some blocks that are connected by a rope. And the question is the velocity or are the velocities for the blocks that are connected by a rope, like in this picture, are they always equal, right? In this picture, if you look, you say, yes, they are. If this 20 kilogram block goes down 1 meter, then this 4 kilogram block has to move 1 meter to the right. Or you might look at this other problem, right, where it's not as simple as this. It's not like one moving horizontally, one moving vertically. In this case, the two blocks are basically on slopes, both different angles. And in this case also, you can say that yes, actually, if block A goes down for 1 meter along this slope, then block B has to also go up 1 meter along that slope. Okay, so in this case, in both of these cases, you can see that the displacements of them per time or their velocities and also their accelerations have to be the same because the rope has no elasticity, and if one is moving faster than the other, there are two scenarios: either the rope has to be stretched or it is going to be compressed, but the rope cannot be compressed, so it loses all of the tension. So in these two cases, the answer is yes, and of course they are, but it's not something you can always say. And one example is this one, which is one of my favorite problems when I do work energy and solve this problem with work energy. Here, the velocities of blocks A and B are not the same. So when B goes down by 1 meter, actually here you can show that block A actually goes up by 1.33 meters. So in this case, A goes up more than B goes down. And so speed of A is bigger than B in this case. Okay, and the answer is, what is the difference? Still, they are connected by a rope passed over a pulley, right? And you might say, well, that's probably because of this angle, and that is right. So is there anything, a general kind of formula or something that I can relate the velocities of the two blocks that are connected by a rope? Is there any general formula for that? Anything that I can find? The answer is yes. So to clarify that, here I added this picture. Let's say I have two blocks A and B that are moving on these two guides, the blue and the green guide. They are attached by a rope, and the velocity of them, VA and VB, are shown, right? You see, parallel to the guides. And the unit vectors that are tangent to the rope at the connections to A and B are shown by U1 and U2. Okay, if that's the case, this is the most general case, then you can show that VA dot U1 should be the same as what? VB dot U2. Okay, what is that? So here you are projecting that VA along U1 and that VB along what? Along basically U2, correct? So one of them is like this if you project it. The other one, you have to continue that and project it this way, so it's like that. Okay, so one of them is like this, the other one is like that, and they should have the same magnitude, because if they don't, that means this point here attached to A is being what? Pulled more than this point that is attached to B, basically being pulled the other way. And if that's the case, then the rope has to be stretched, which is not possible. So this is your answer. Okay, and in this case you can see that because this is U1, this is U2, or you can say upward, doesn't matter, but we do it in the same direction as velocity. So this is V of B, and This is V of A. So if you can see here, because U1, U2 are parallel to their corresponding V's, VA and VB, when you apply this, the projection is simply going to be magnitude VA equals what? Equals magnitude VB, and that is what we expected, right? So here it's very obvious. Or if you apply it to this case, again, that's the exact same thing. If you look here, again, this is V of A, right? This is V of B. And here, this is the unit vector UA or U1. And this is the unit vector what? U2. So again, you see that they are the same what? They are the same direction. So you will get to the exact same thing, that VA has to be the same as VB. Because VB and U2 are parallel, VA and U1 are parallel. But in this case, in this example, that is not true. If you look here, this is VA, this is VB. But if you look at the cables, this is what? This is U2, but U1 is this angle. You see, that makes the problem not as simple. So here you have to do dot product between VA and U1. You need this angle. You need this angle theta. So here, if you say VA dot U1 is the same as VB dot U2, well, VA dot U1 is going to be simply magnitude VA times cosine of theta, but magnitude, the VB dot U2 is simply magnitude VB. You see, so this is the relation between them. And since this theta changes as this block A goes up and B goes down, this distance 2 meters stays the same, but this 3 is gonna change. So your angle is, right, when you go here, when you go there, right, your blocks goes up, then your angle gets bigger, and so the relation between VA and VB is not constant. It does change on the cosine of that angle. And what is the cosine of that angle? Let me show you something interesting here, because the way I derive the relation between VA and VB in my class is a little bit different, and I'll show you how I do it, but you can also do it this way. So what is cosine of theta? Well, if you look at this triangle, if you look at this right triangle here, clearly cosine theta is this distance, whatever it is, divided by the hypotenuse. Now, this 3 is the initial distance from A to this pulley. As this A moves up, it's going to be different. So here you can assume that right now A has gone up like this, and this is now your rope, okay? If that is the case, and this displacement from here to here, you show it by YA or delta YA, then in this right triangle that you have left, if you can see this right triangle, then your adjacent to theta is going to be 3 minus YA, and your hypotenuse is going to be square root of what? It's going to be square root of basically 2 squared plus 3 minus YA squared, right? So you get VA times 3 minus YA, the adjacent, divided by the hypotenuse. This is equal to VB. And as I said, the hypotenuse is 3 minus YA squared plus 2 squared, right? Because this distance from here to here is 3 minus YA, and this other distance is 2. So that is the relation you can find between VA and VB, okay? This is the relation, and you clearly see it does depend on the location of A. Now, the way I do it in class is a little bit different, and I derived that for you as well here. So you see that this formula I gave you, this one, is actually very effective, and you don't need to do all this process that I do here. So this is how I do it in class. I say, well, assume that A goes up and B goes down, right? So let me clean up these. So A goes up to there, and let's say B goes down to here. So this becomes the new cable, this thick blue cord. Yeah, so B goes there from here, and A goes up here. And here, this is Y of B. So it goes down by distance Y of B, A goes up by distance Y of A, assuming that B is quite a bit heavier than A here. Now I say the total length of the rope in situation 1, which is this black one, is equal to what? Is equal to this hypotenuse plus something around the pulley plus this distance from here to here. Now that distance, I don't know how much it is. Nowhere in this problem it's given to me, so I just call it X. And this one around the pulley, I call it not Y, maybe something else, or let's call this X1, call that X2. So X1 and X2 are the distances I don't know. So this hypotenuse is clearly square root of 3 squared and 2 squared, right? So it is going to be this plus X1 plus X2. Then I calculate the length of the rope in situation 2. So it is, again, that hypotenuse, which we just calculated, this denominator, plus what? Plus something, again, around the pulley, which you can approximately say that's the same as X2. It's not perfectly X2, but very close to X2. And then this distance from here to here, which is clearly what? X1 plus YB. By the way, this X1 should really be measured from here to the bottom of B, like that. That is X1. So X1 plus YB. And now, since X1 and X2 are constant, and remember, these two have to be the same. They are the same entity, they have to be equal, right? Because the length of the rope does not change. So if you set them equal and get rid of X1 and X2, right, you get what? You get square root of, this is 13, equals square root of 3 minus YA squared plus 4, or 2 squared. And now what you need to do from this relation is to take a time derivative. Well, derivative of constant is 0. Derivative of YB becomes VB, right? Or Y dot of B, plus it's a derivative of a square root, which is going to be the time derivative of inside of it divided by 2 times the square root. And what is the derivative of inside of it? Well, that's constant, that's 0. This is a something squared, so it's going to be 2 times the term inside of it times the time derivative of inside, which is negative Y dot of A, which is V of A. And now you can get rid of these 2's. And then you can basically take this term to the other side. If you do so, you can get rid of that negative. And if you do that, you will get that VB equals VA times what? 3 minus YA divided by the square root. And this is exactly the thing that we found right here. Look, because this entity is cosine of theta. You see, they're the same thing. So now if any situation they gave you like this is the answer. Okay, VA.U1 equals VB.U2. So hopefully this video was useful to you. I'll see you in the next lecture. Thank you.